Hello students, this video lecture will cover section 4.8, Newton's method. As you may have noticed from your time in algebra and now in calculus, one of the most typical problems that we see in all of mathematics is finding the roots or zeros of a function. Now remember, the roots of a function are the values of x that satisfy the equation f of x equals 0. In other words, these are the points known as the x-intercepts of the graph. One of the most important root finding problems that we've seen this year is finding the critical points of a function of f. In other words, finding those points where the derivative is 0. So remember, the roots of f prime are the critical points of f. Newton's method is a method for approximating the roots of a function. And so the first question that comes up is usually, why do we approximate? Well, we can find the roots of a quadratic by using the quadratic formula. And we can find the roots of a linear function by using algebraic methods. Just like we've used the quadratic formula, there are formulas where we can find the roots of a cubic and quartic function. However, once we get into polynomials of degree 5 or higher, analytical methods no longer give the roots. So when analytical methods don't work, which is the majority of the time, we have to have another approach. Those approaches are numerical methods, and one such method is known as Newton's method. Typically when we derive Newton's method, it's done geometrically. If we assume that r is a root of function f, and we want to approximate this root, what this means is the value of the function at r is 0. We have to assume that f is differentiable on some interval containing r, and we take x naught, or x sub 0, as an initial approximation to r that is obtained by some preliminary analysis. So basically we're taking our first guess at something that's going to be close to the actual value of the root. So a line tangent to the curve, y equals f of x, at that initial point, and the value of the function at that point is drawn. The next step we do is find the point x1 comma 0, at which the tangent line intersects the x-axis. And then we use that new value x1 for our new approximation of r. So you can see here our initial approximation is this value, and we draw the tangent line and find some new value, and this value is now x1. So then we use x1 as our approximation and proceed again. That allows us to find x2. A third time allows us to find a root closer, or an approximation of that root closer. A fourth time. And by the fifth time you can see we're actually very close to the true value of the root. So if I take this value of the root and draw it actually closer to the true value, in other words, if my initial approximation is better, you can see that after 2 iterations we're very close. Our third iteration, fourth iteration, and fifth iteration take us almost to the actual value. In fact, the closer our initial estimate of the root is, the faster our convergence to a better approximation of that root. So this two-step process continues and eventually gives us a sequence of approximations. Ideally, our sequence is getting closer and closer, converging to the root r. Several steps of Newton's method and their convergence of their approximations to the root are shown in figure 4.7.1. You can see here's our initial approximation, which is pretty far from r. Our first tangent line gives us x1. We use x1 and draw a new tangent line. We use x2 and draw a new tangent line. And you can see that our value is getting closer and closer to the true value of r. So what we want is a formula that's going to capture this process. If we assume that we've computed the nth approximation, or x sub n, to the root r, and we want to obtain the next approximation, or x of sub n plus 1, we draw the line tangent to the curve at the point. Its slope is given by f prime of x, and using the point slope form of the equation of a line, an equation of the tangent line at the point x sub n, f of x sub n, is given here. We have y minus the y coordinate equals the slope times x minus the x coordinate. And that comes from point slope form. We find the point at which this line intersects the x-axis by setting y equal to 0 in the equation of the line and solving for x. This value of x becomes the new approximation, x sub n plus 1. So here we've set y equal to 0, and x becomes x sub n plus 1. So if we solve for x and call it x sub n plus 1, we find that x sub n plus 1 equals our current approximation minus f of x sub n divided by the derivative of f of x sub n. And here we have to assume that the derivative of x sub n is not equal to 0. So the general step of Newton's method is given by this formula. And we repeat this step for 0, 1, 2, 3, so on and so forth, until we meet some termination condition. And we'll discuss those in a minute. So our procedure for Newton's method for approximating roots of some function is to choose an initial approximation as close to the root as possible. And then for n equals 0, 1, 2, and so on, we follow this formula so long as the derivative of x sub n is not equal to 0. And we're going to end the calculations when a termination condition is met. At this point, quick check 1 asks you to verify that setting y equal to 0 in the equation given here and solving for x gives the formula for Newton's method. You can take the time to do that, and if necessary we can verify that formula the next time we meet. Here example 1 asks us to apply Newton's method to a given polynomial function. So we want to approximate the roots of x to the third minus 5x plus 1 using 7 steps of Newton's method. We're going to use -3, 1, and 4 as our initial approximations. So here you can see -3 is pretty far off from our root. We might actually want to start with a point closer to this value, but -3 is not too bad. 1 and even 4. So the first thing we do is we need to find the derivative of our function. So here the derivative of f is 3x squared minus 5. So we want to plug this into Newton's formula. X sub n plus 1 equals x sub n minus f of x on top, f prime of x on bottom. And then you can see this is the formula simplified. So here we have an initial approximation of -3. So we're going to plug -3 into our formula. So we have 2 times -3 to the third minus 1 over 3 times -3 squared minus 5. And so starting with -3, after our first iteration, we have -2.5. So the second approximation takes the result of the first approximation and it plugs it into the same formula. So here we have 2 times -2.5 to the third power minus 1 over 3 times -2.5 squared minus 5, and that gives us an approximation of -2.345455. Table 4.5 shows us the result of the first 7 approximations for each of the starting points, -3, 1, and 4. So you can see after the first approximation we were at negative 2.5. The second approximation gives negative 2.345455. And very quickly, the fourth, fifth, sixth, and seventh approximations are all the same thing. Same thing with starting at 1. Our approximation goes to negative 0.5, 0.294118, 0.200215, and then by the fifth, sixth, and seventh approximations, we have 0.201640. With 4, we have 2.95, 2.38, 2.166, 2.129, and then 2.128420, 2.128419, and then 2.128419. So you can see that after a maximum of 6 iterations, our starting points, while not perfect, negative 3, 1, and 4, converge to a value that is very close to the actual root. By looking at an actual graph, we can start at negative 3 and show that after the first 5 approximations, our root is very, very close. And you can see here that to 5 decimal places, the fourth and fifth approximations are exactly the same. Starting with a value of 1, our first approximation puts us at negative 0.5. So our estimate is far enough off of our actual root that we go to the opposite side of the y-axis. Our second approximation brings us back. Our third approximation, 0.20021, 0.20164, and finally the fourth and fifth approximations are exactly the same, to 5 decimal places. For root 3, we know that the value is just north of 2 by looking at this graph, but we chose an initial estimate of 4. Our first estimate gets us just under 3. Our second estimate takes us much closer to close to 2.4. Our third estimate looks very close to our actual root. And our fourth and fifth estimates get us even closer. You can see for the first time our fourth and fifth estimates aren't exactly the same, and that's because our initial guess of 4 was so far off. Here your book gives 2 methods for when to stop calculating Newton's approximations. Ideally, we'd like to calculate the error in x sub n as an approximation of the root, which would be the quantity x sub n minus the actual root, and then take the absolute value of that number. But since we don't know the actual number for r, we have to have some other method. In this case, the method that I agree with is presented first. Take multiple iterations, take them and consider the first, say, 6 points after the decimal point. Once you have 6 places after the decimal point that agree, you can say that those 2 successive iterations are probably a very good representation of the actual root itself. Newton's method generally finds a good approximation to a root after, let's say, 5 to 6 iterations. So if you haven't found 2 iterations that agree after, say, 10 attempts, it's probably a good case to stop. Newton's method's not going to find an approximation of that root with the accuracy that you're looking for. Another great thing to use Newton's method for is to find the intersection point of 2 curves. So here we want to find the point at which y equals cosine of x and y equals x intersect. So here we have y equals cosine of x, and here we have y equals x, and we're looking for this intersection point right here. The graphs of these 2 functions, g and h, intersect at points where the x coordinates satisfy that g of x equals h of x. Or we can create this new function f such that it's g of x minus h of x and set that equal to 0. In other words, finding intersection points is really just a root finding problem. In this case, we're looking for the roots of f of x, which is cosine of x minus x, and we're trying to find the point at which that's 0. Here we see that the two curves have one intersection point, and its x-coordinate is between 0 and 1. So that function has a 0 somewhere between 0 and 1. So we take a guess at what it is. Your book says to take an initial approximation of 0.5. Here, just to make my life easier, I might choose 1. But let's see what happens. So here on the top, you can see we have the function of x sub n, so cosine of x sub n minus x sub n, over the derivative, and in this case, we have negative sine of x sub n minus 1. So here you can see the formula simplified. So they plug in 0.5, and the first iteration kicks out 0.755222. By the second iteration, we have 0.739142, and the third, fourth, and fifth iterations all agree to 6 decimal places. And you can see the book is calculating residuals here as well, the second method to determine when to stop. So then, after 4 iterations, the approximations agree to 6 digits. So 0.739085 is a good approximation of the root. Therefore, the intersection point is going to be at approximately 0.739085, and the y-coordinate is going to be 0.739085 also, because remember that this point has to lie on this line y equals x. Example 3 talks about finding local extrema, something that we've talked about previously. Here we want to find the x-coordinate of the local maximum and local minima of the function x to the fifth minus x to the fourth plus x squared minus x on the real number line. So we take a look at a preliminary graph, and we can see here that f has a single local maximum somewhere between -1 and 0, and a local minima somewhere between 0 and 1. So remember, this involves the first derivative test. So we're going to take the derivative. We have 5x to the fourth minus 4x cubed plus 2x minus 1. We're going to set this equal to 0. Here your book gets a little bit lazy and they say let's approximate these at -1 and +1. We can see those approximations are pretty far off. But watch how quickly these converge. We have after the first iteration -0.8, 0.706, 0.6844, 0.6833, 683350, 683350. So the fifth and sixth iterations are the same for the local maximum. Now for the local min, we started at 1, we go to 0.8, 0.6684, 0.614669, and then by the fifth and sixth iterations you can see again that Newton's method agrees to 6 decimal places. So this method converges fairly quickly. The final part of this section covers some of the pitfalls of Newton's method. Typically, if we take a good initial approximation, Newton's method will converge to a root within, like I said, 6 to 7 iterations. But when it doesn't work, it's usually very interesting to watch it not work. So typically, one of the things that happens is the denominator, or f prime of x sub n, will end up being 0. That'll cause the whole system to break down. The other thing is, whenever it gets very close to 0, whenever the derivative of x sub n gets close to 0, our method's going to be very slow to converge, or it might not converge at all. Now this has to do with sequences and series, something that most people study in a pre-calculus course. But let's see what happens. So here we have f of x, which is 8x squared over 3x squared plus 1. We're going to use Newton's methods with initial approximations of 1. We'll look at another situation where it's 0.15, and we'll look at another situation if you chose 1.1. Now you'll notice here that since we have a second degree polynomial on top and a second degree polynomial on bottom, this method is not really necessary because this is going to have a single root at x equals 0. The interesting thing here is really just to watch Newton's method at work. So here you can see the simplification of Newton's formula, and let's take a look at the different iterations. So our first example has an initial value of 1. So we choose 1 and we draw our tangent line, which gives us negative 1. When we plug negative 1 into our formula, it gives us positive 1. Positive 1 gives us negative 1. Negative 1 gives us positive 1. Positive 1 gives us negative 1. You can see here that we're alternating between positive 1 and negative 1. So in this case, we'll never actually see a convergence. Now, this picture is zoomed in considerably closer, but it's actually the same function. Now you can see with an initial approximation of 0.15, something that's actually very close to 0, our function will eventually converge, but it converges very slowly. So you'll see we have no agreeance even after the 5th iteration. And for our final example of a pitfall of Newton's method, let's start with an approximation of 1.1. After our first iteration, we end up at negative 1.446. Our second iteration takes us to 3.8, which takes us to negative 81. And you can see that our approximation of the root is increasing in magnitude at a very high rate of speed. So the three different types of pitfalls: our approximations may cycle. That's the example where it was bouncing between positive 1 and negative 1. They may wander. They may converge very slowly. This is the example where we used 0.15. Or they may actually diverge instead of converge. This is the example we just saw with 1.1. So let's see what would happen if we used an initial approximation of 0.3. Our first iteration takes us to 0.109, 0.05, 0.02, 0.01, 0.00653, and you can see that after 5 iterations, we're not super close. So let's take our initial approximation. If we take it as close as this system will allow us, we can see that this function is going to converge very slowly to its root. So with certain functions, Newton's method's not going to work very well. And this function's one such example. And that concludes this video lecture on section 4.8, Newton's method.